Welcome, everybody. Today, we're having a conversation about the cosmos, about a quality of the cosmos that we've had a lot of conversations about over the years in World Science Festival programs, because in the last 20 years, 25 years, it really is perhaps the most surprising of all cosmological results, which is simply that not only is the universe expanding, but it's expanding ever more quickly. It's accelerating in its expansion. This is something we learned about in 1998, as we'll discuss in our conversation here today. But the reason why we're focusing upon the so-called dark energy, which we believe may be responsible for the accelerated expansion of space, is that, as you may have read, there are new observations, remarkably new observations. They're still tentative, to be sure, but there's at least a hint in the data that aspects of the dark energy that we have long since had in place may need to be rethought. And I don't think I'm giving anything away, but spoiler alert, where we will get to in this conversation is at least the possibility that the dark energy is not constant, that it may change over time. And that would be a real revolution in the way that we think about cosmology. As we'll discuss, it would have profound implications on the far future of the cosmos, what things will be like well beyond any cosmological era that we have direct access to. But when you're trying to understand the entirety of reality, knowing things like what will happen in the far future is something that really matters. And all of these hints or all of these suggestions are coming from a truly remarkable technological feat in the work in observational astronomy that has allowed us now, and by us, I don't mean me, I mean the team whose director we're going to talk to in just a moment, to measure the properties of distant galaxies with fantastic precision at a scale that is really unprecedented in cosmology. And that's really what has allowed these new results to surface. And so it gives me great pleasure to bring into the conversation Micheal Levi. He's a senior scientist in the Lawrence Berkeley National Laboratory in the physics division there. And he's the director of what's known as DESI, the Dark Energy Spectroscopic Instrument, which is the technological development that has allowed these results to come to the fore. And as we will discuss, these new observations may go away in time, or they may change everything we think about how the cosmos has evolved. So, Micheal, please join us, and thank you for being here today. Where are you at the moment?
Well, thank you, Brian.
From?
Well, I'm currently in my office at the Lawrence Berkeley National Laboratory. It's up in the hills in Berkeley, just above the UC Berkeley campus.
And
Beautiful.
that is the epicenter for the DESI experiment, right? The experiment itself is not there. I guess it's in Arizona,
Right.
and this is where all the data analysis happens. And look, I want to get into the details of the actual experiment and the equipment that you guys have built, but I think it's really good to give our audience, although many in our audience are well versed in some of the cosmological ideas that I just
Mhm.
briefly made reference to, but I think it's always nice to hear it again. So I don't know what the right moment in cosmological history to go back to,
Yeah.
but maybe sort of 1930-ish, when we had the first observations that began to give us insight into the expansion of space. So that was, of course, Edwin Hubble. And one of the suppositions that I think most people brought to that result is, okay, it is mind-boggling and perhaps unexpected, except to a handful of people, that space is expanding. But everybody thought that the expansion would be slowing down, right? I
Well, of
don't think
course,
anybody
because
really
well,
questioned it.
no, and I think because of gravity, we assumed. In fact, I remember talking to my colleague Saul Perlmutter, whose office is just down the hall, and I know you interviewed him. Um, and of course, he was one of the people in the discovery of the accelerating universe. Of course, he was on a quest to measure the the number associated with how we were slowing down and probably going back to a big crunch. I mean, we just and of course that was the answer. And I think we had locked in to sort of a model where the universe was either going to kind of just drift off and slowly almost stop, out at infinity time. At infinite time, it would just come to a standstill, or it would go back and do a crunch. And I don't think we knew. And so that was the interest in the experimentation was, well, okay, exactly how is that? How do we finish? Do we finish in another crunch where everything recollapses on itself? Is there enough matter for that to happen? Inconceivable that it would be expanding at an accelerating rate, which of course was an amazing discovery in 1998. And I
Yeah.
think that all the years before that, that I can remember from my entire professional career, that we just assumed that the end was going to be in a fiery recollapse, something like that. I think that was kind of the assumption.
And so when you first heard about Saul's result, and of course it was also Adam Rees and Brian Schmidt, they all shared the 2011 Nobel Prize for this work. When you first heard that their results seemed to suggest that the expansion was speeding up, I mean, did you believe it at first, or
Well, first of all, I mean, I think the initial measurements were, which may not have been public, but we certainly heard the rumors through the walls here.
yeah,
On a smaller number of supernova. Well, these are hard measurements to make. In particular, it requires measuring the brightness of an object in a manner of a standardized candle, and so you're counting on the supernova, type 1a supernova, to collapse in a manner that they would always give off the same amount of light, and then you could calibrate against that. That's a standard candle. So that was the assumption. Well, maybe there's something wrong with that assumption. There's dust in the universe that makes it more difficult for you to do that measurement and harder to correct it. So could there be something wrong? And these are subtle measurements, and they're hard to do, and you're doing it across enormous spans of time, across wavelength. For an instrumental perspective, it's harder to do when it's across wavelength. And so these are tough measurements. And of course, it was the first one, and the answer was wrong, right? I mean, like, this would have just completely dumbfounded everyone, right? So of course, it required more data, and he got more data, and then after 42 supernova and across a lot of tests, they published. And of course, they had colleagues that also published. You mentioned the multiple winners of the Nobel Prize. I mean, so it's two groups. The two groups having the same answer, went a long way to assuaging the concerns of the community that this was right. I mean, I think if it had just been one group, and then you'd say, well, yes, but is it true?
right.
But having two come at it from different experimental approaches, I think, was very, very important.
Yeah, I think that's why, in some way, I'm a theorist and not an experimenter, because, at least in theory, once you make your assumptions and you make them clear, then it's just deduction. And so as long as you don't make an actual mistake in the calculations, you're on solid ground. Whether it's relevant or not to the world, whatever you found, that's a different question. I don't think I'd ever have the confidence to have a startling result like the expansion is speeding up and ever trust it enough to go out into the world and make a statement.
I think you have to be a little paranoid to be in our business,
Yeah.
because you have to ferret out those mistakes. I mean, I think that you're right that it is a terrifying business. In fact, we just published some papers which we're going to talk about, and I can assure you that everybody, before you hit send, you're pretty worried. Did we do all the checks that we needed to do? And the list is yards long of those kinds of checks. And so, yeah, you try to eliminate potential sources of error, or just outright blunders. And so we have methods for doing that. And of course, our experiment, we tried to find something that was also like a standard candle, like what Saul had with the supernova, but something that was even simpler that we could find, so that we could do a more refined, even a more refined search into this question. So that's what we did, and of course, simple. I'm a physicist. I'm not an astronomer. I'm a
Yeah,
physicist.
sure.
Physicists are reductive. We like really simple approaches, simple answers, simple ways of doing things. And so we think we found one that was pretty good. And then you have fewer opportunities for making error.
Right.
So that is very important. And of course, that is part of the art.
Yeah.
Yeah,
And
I,
just to give
I did
people
my
a
my physics homework. I got
yeah,
those factors of two errors too. So just
yeah,
like you
right.
did.
We know them all too well.
Yeah,
But
yeah,
just to give everybody a sense, again, I think most of our audience is familiar with the idea of standard candles. But just quickly, if you're looking at something in a telescope far away, to determine its distance is non-trivial. Naively, you'd say, well, the dimmer it is, the farther away it is. Well, yeah, sure, but it could also be dim because it's intrinsically dim, or it could be dim because it's really far away and that's making it look dim. And so if you have these standard candles where you know how bright they are, like a 100-watt light bulb, then based upon its apparent dimness, you can figure out how far away it is. So you made reference to the Nobel Prize winning work that they use supernovae
yeah.
because their physics was well understood, so their brightness is well understood in terms of how their brightness changed over time and so forth. We don't have to get into the details, but what was your standard candle then? You mentioned that you sought out one. What was it?
So we have a standard ruler. So instead of it being the intensity of light, which you now have to like calibrate that against something, um, we have a yardstick, a cosmic yardstick, and it happens to be related to the Big Bang. And at a moment of time, about 400,000 years after the Big Bang, all of this very hot plasma that existed after the Big Bang, of the electrons and protons all floating around, they recombined into neutral hydrogen atoms, and all the light streamed out. All of a sudden, this became transparent, and so we have this moment in time that we can look back to. Quite a number of experiments have looked back at this moment of time, which is reasonably well understood. Um, and we found that in this at that moment of time, you have basically bubbles of sort of form that have the shape of the universe at that moment in time, and it's called baryon acoustic oscillations. Imagine the universe had this was like a drum that somebody was pounding on it. Yeah, it was a big bang pounding on the drum and saying, "Here I am," and it forms. You can think of it as sort of bubbles or froth that are of a standard size that represent the size of the universe at that 400,000 year period. And now that is imprinted on the distribution of galaxies. So where there was a hot spot in these you get more galaxies. Where there's more density, you get more galaxies, and where they're under density, you get fewer.
Yep.
And you can find that in the data through correlations. It's not a huge effect; it's 5 or 10%, but
Right.
it's very definitely there. That's our standard candle, because that thing is now an object who then stretches with the universe as the universe gets bigger, and so we
Right.
can just follow uh, that that unusual distribution of matter. As I said, we call it baryon acoustic oscillations, or acoustic oscillation baryons, in this case being hydrogen.
And again, just to flesh out a chart, so you got the baryons, you got the photons. Photons want to stream outwards. The baryons gravitationally want to fall inward, and so you get this oscillatory behavior.
Phenomenon, right?
And then, at about 400,000 years, you say the baryons join into neutral atoms. The photons are released, and at that point, the acoustic oscillations kind of get frozen
Frozen
in,
in, yeah,
and you measure the size of those.
of that shape. So it's fairly simple, and that gets frozen in. It got frozen in long ago. Nothing else happened in between, other than these are now drifting apart. Everything is
Yeah.
galaxy formation, but everything is just drifting apart. So that phenomenon got locked in very, very long. At year 400,000, and okay, now then we run this movie forward 13.6 billion years forward to today. And so what we're trying to do with our experiment is to be able to replay that movie, go back
Yeah.
in time and watch these bubbles sort of expand with the expansion of the universe. So that's our yardstick. you as a theorist can sit down and say, well, how big should that yardstick be? And, there's a number, and we can just, go to the computer and see, well, how should this propagate out given different theories of cosmology?
And can I think about that ruler as roughly being the dominant distance between galaxies at a given epoch? Is that an intuitive way that I can think about that?
Well, it would be, well, first of all, it's about, if I stick my thumb up on the sky, it's about that big.
Yes.
And so that's maybe, that's one yardstick. So it's in one direction, it's an angular distance.
Yes.
Um, and of course, along the line of sight, it's the same distance rotated, but now it's along the line of sight. And that's something that we can measure. And it's you just have to have a lot of galaxies to be able to measure that. So it's not so much an individual galaxy spacing, but statistically speaking, of a collective.
Yeah.
So if I have one galaxy here, okay, got to get in the. If I have one galaxy here, I'm going to have a propensity if it's 400,000. If it was way back then, it's 150 megaparsecs away is the astronomical distance, that I have a propensity for having more galaxies over here. So in sort of in that kind of sphere
surrounding it. Yeah.
Sphere surrounding. So and I said, it's statistical. It's at a sort of a 5 to 10% effect, but it's something that we absolutely definitely see. And you don't need a huge number of galaxies to do it. Previous experiments, like the first experiments that we're doing this on tens of thousands of galaxies. We're in the millions. The data we just published on was 6 million galaxies, and we're going up in numbers on that. So
yeah. So I'd love to get into the details of that in half a second, but just a quick summary is, so you can measure this standard ruler and how it's changed over time. So that gives you an expansion history of the cosmos.
Right.
And your goal is to see, how has it changed over time? Is it compatible with what your colleague Saul Perlmutter and the other supernova teams found, that the expansion rate is speeding up? And is it compatible with the explanations that they had for the particular measurements that they made? And so were you thinking about doing this work? Is this a recent undertaking, or when Saul's results came out in 1998, did it immediately get you thinking, let's try to dig in more deeply? I mean, what's the history of your thinking on this?
Well, interestingly, because Saul was my colleague, and I was just so fascinated by this back in 99, that Saul and I started thinking about, well, what do we do the next experiment on this? Let's start looking at a refinement in this. And we came up with this idea of a satellite. It was called SNAP at the time. Actually, first time I ever met you, I think Saul and I it was in an airport. I think we were in Washington, or
this is familiar.
And we came to you and we said, Brian, so help us understand, you're the theorist. You tell us the answer. What should we be looking for? And it became very clear.
Did I say anything smart? Geez,
I think you did, actually, because the thing that was apparent, I think, at that time was, well, what we called at the end of Saul's experiment, what we called this phenomenon of this accelerating universe, is it was being driven by a cosmological constant, the cosmological Einstein's greatest point, cosmological constant, something, that property of the vacuum that was causing this acceleration. But it was a number, and for physicists, just who ordered that? I mean, that wasn't on the menu. And
because it's such a weird number.
It's such a weird number. Where did it come from? Do string theorists, can they calculate that number? And the thing that I think you pointed out, and other theorists pointed out even early on, was, is it time dependent?
Yeah.
How do we know that it's a constant? I mean, you guys, you got a number, you fit a number to it, but that's because you didn't have enough data to know, anything else.
Yeah.
And so I think that's what really, I think we latched on to 20 years ago now. Yeah. That is it time dependent?
Right.
We've never had the data to ask that question.
Right. And in fact, just to give the audience a clear sense, I mean, the amount of this, maybe you should quickly say, so Even Einstein himself, back in 1917, introduced into his equations this idea that you make reference to, the cosmological constant, which you can think of as an energy suffusing space that gives rise to repulsive gravity, pushing outward. That's music to the ears of a more modern day cosmologist, because if things are accelerating outward, you need something to push. Einstein introduced it for the wrong reason. He wanted to balance the ordinary inward pull of gravity to give a static cosmos. We know that that's incorrect, but the idea of energy filling space, pushing outward might be right. But as you make reference, when the data came in 1998, the amount of dark energy needing to explain the observations in the right units, the natural units, is a decimal point, and then 120 zeros and a one.
Yeah.
And like you're saying, when a theorist or an observationalist or an experimentalist or even any rational person encounters a number like that, you have to say to yourself, how can we explain a number like that? And you're right. Our initial reaction as theorists when we see a number like that is, maybe you're not trying to explain that number. Maybe you're trying to explain an evolution that takes you to that number momentarily on cosmological timescales. And so absolutely, that was certainly a natural idea that I think many people went to at the time. So you and Saul then cooked up an idea to begin to possibly test the time dependence, but through satellites as opposed to Earth-based.
Right. It was called a SNAP, a supernova acceleration probe. We actually proposed that to the government. The government said that's a great idea, but in the case of government, I work at a Department of Energy laboratory, so our part of our agency was Department of Energy. Department of Energy said, well, satellite, there's another agency that might be involved called NASA. Then became the Joint Dark Energy Mission, and then that went to the National Academy of Sciences. Some years later, after that, we're talking fair amount of time, and then it became something called WFIRST.
Yep.
Which is now the
Roman,
which will launch in 2027. So this is happening, but this is now this took on a life of its own. So
and so did you leave that project or?
Yeah. Well, at that time, it really got I was the project scientist for the Department of Energy side of the joint. For the Joint Dark Energy Mission, but once it no longer was a Joint Dark Energy Mission, WFIRST became a NASA project. There are costs and other things associated with that.
But was that disappointing? Was that?
Oh, well, I'd worked on this for a long time, so for me, it was personally disappointing. On the other hand, it was gratifying to see that this was moving forward.
Yeah.
So, you take your professional knocks where they are. On the other hand, we had, I got into this area, and then we discovered, well, there are many ways to look to try to do experimentation. And one of the methods that came to the fore during that time period was the realization that you could look for baryon acoustic oscillations as a standard ruler. And yes, this is part of these space missions now to look for that. But lo and behold, you can do that from the ground too. Mm-hmm. And as you know, if you can do things from the ground, you get to do them faster and they're less expensive. And so we again proposed to the government. We've got this project called DESI. Well, actually, the government gave it. We had a different name for it, but the government turned around and said, yes, this is a good idea. We had community panel process to come to this. And so we ended up with the dark energy spectroscopic instrument in 2012.
And so maybe you give us a sense then of what that instrument is like and how it goes about doing these measurements.
Yeah. All right. So the experiment that we proposed and got to build, which was wonderful. You don't always get to build the experiments that you want. So this isn't the first time somebody's tried to go out and measure baryon acoustic oscillation, measure this distribution of galaxies. At the heart of it, it's really a very simple idea. It's just a map. But it's a map in 3 dimensions. So 2 dimensions are the angle on the sky, and the other is the redshift. You can think if you knew the cosmology, it would be an actual distance, but it's a redshift. So you get a three-dimensional point. It's a three-dimensional. It's a map. So you feel a little bit like an old explorer. I'm making a map. It's not a map of the coastline of some continent, but it's a map of the universe.
Yeah.
Well, it's a map of the universe. In our case, a map of the universe that goes back 11 billion years from now to all the way back there. So, and then you, of course, you want a very accurate map, and the map has to have sufficient density of galaxies in it that you can see this ruler, a Baryonic-Kuiper oscillation, in there in the distribution of galaxies,
and see the ruler changing over time.
Exactly, and be able to fit like, okay, I want to see a time distribution, because we now want to see not just what is it a cosmological constant, but is it time varying? Is there something about this that's different at 11 billion years than it is today, or at 5 billion years, or 7 billion years? And you need a lot of data to do that. So our predecessors did this with a small amount of data and got a little bit of information saying, it's consistent with what was observed with the supernova. Okay, well, that's great, but we wanted to go further than the supernova. So we needed a lot more galaxies, going a lot deeper.
So your goal is to measure the spectroscopic measurements on individual galaxies at a variety of distances, therefore at a variety of different moments in time.
Yeah. So you brought up one of the dimensions, which is which we get at through spectroscopy. So we find this particular emission line or emission lines in galaxies are very active, and they've got all things going on with them, which we don't care about. I mean, we're just a dot on we could not care less what kind of galaxy it is.
Right.
We just want it's just a dot, which is representing a distribution of matter in the universe. So it's just a dot. And but we need to get the redshift. Okay, so we fit it to some template that says, okay, it's at a redshift in this number. But everything, all these galaxies are emitting something similar in terms of, it's got an oxygen line, it's got a hydrogen line, it's got this line. So these are elemental lines, and they're not hard to determine what their redshift is. In other words, how far away they are. So not, it's conceptually not that complicated. But that's, the devil is in the details, as they say. So the last experiment, Sloan Digital Sky Survey, the devil in the details is that you take an aluminum plate,
drill holes in it.
What they did, they took aluminum plates, they drilled holes in them, and then aluminum plate with the holes drilled in were stuffed with fibers, fiber optic cables, and the fiber would grab the light from the galaxies. So you take this thing, it was a cartridge. You put it in the focal plane of a telescope. The light would come down. The drilled holes corresponded to the positions of known galaxies. You pick off the light from those galaxies, it would go off to a room go off to a spectrograph that would now tell you what the redshifts were. Okay, so you have to have a predetermined notion of where everything is located, so you can drill the holes on a drill press, basically. And they had thousands of these, and they could do 8 changeovers a night, and they started out, I think, with 500 of these plugs of these fibers, and they ended up with 1,000 by the time they were in. And technicians, had to do that work, and they were very good at it, and they really were excellent. But they're just sort of limitations to how many galaxies you can do, and the experimentation that's possible with that. And so it had to also be a smaller telescope where you could actually install this and whatnot. And so it wasn't a very big telescope, so it couldn't go that deep, and couldn't make that many observations. Well, that was the last one, but they did very, very well. So we're trying to figure out, well, how do we do better? And so then we ended up with a robotic instrument. And other people have done or attempted to do robotic instruments where the location of these fibers are determined by computer. So
you're not drilling holes any longer.
We no longer drill holes. We actually have a little. And I my little prop here is this is one of the robots. We have 5,000 of these robots, and they twirl around. They position a fiber. Um,
Yeah, I think we have a beautiful animation probably
oh,
of
oh,
yours.
fabulous! Oh,
Yeah,
fabulous! Yeah, there it is. So this is our focal plane. It's got 5,000 of these robots on it. They're divided into 10 wedges. You can see them just for assembly's sake.
sure.
And then they twirl around, and so within their patrol radius, they can be commanded to go to where a known galaxy is. So we had to, before we did the survey, we had to know, well, where are we going to look, because we had to put our fibers on known locations so that we could get the redshifts. So you and you can see, I think, a little sticking up there, the little fiber, the little white little things that look like little white swords, or those are the fibers sticking up, and those are what pick off the light. I mean, it's all about getting the photons, giving every last photon from 11 billion years ago. There aren't that many.
And how long does a given fiber need to point at a given galaxy to
So
make its measurement?
so we sit for about 20 minutes.
20 minutes.
In this movie, you've got it. It looks like it's a dance. No, they orient themselves to the correct location. We actually take a picture of that and say, well, okay, did you get to the right? Did you get exactly to the right position? Maybe you didn't. Okay, we'll make a little adjustment till it's exactly right, and then we open the shutters. So an actual mechanical shutter, the door opens. We take in the light, and then we sit there for 20 minutes, bringing in the photons, and they're not that many when they're coming from 11 billion years ago.
I
Um,
mean, how many photons are you detecting per galaxy?
well, over a course of 20 minutes, thousands. But
Which
um,
is, seeing that they're about 10 to the 20 per second coming out of the bulbs above, it's that
yeah,
tiny,
these are
yeah,
small numbers, and we had to build our own sensors. Okay, another one of my props. This is an example of a wafer that has a sensor on it. Here's the large sensor that we use, and this is capable of sensing one or two photons at a time.
I see.
So really incredibly sensitive. We have to conserve every possible photon that we can get, because it's so very dim, and we're looking so very far back in time. So that's part of the art of doing this. But
I
where
mean,
we were,
was it hard to get there? I mean, it looks like a technological marvel. I mean, were there many fits and starts to
it's
get to
kind of beyond comprehension. So this has a quarter million moving parts.
quarter of a million moving
Quarter
parts?
million, quarter million moving parts. Yeah, quarter of a million. So
Mm.
it's a lot of moving parts. We were talking earlier about being worried about what things can go wrong in an experiment, and what it's like. Well, guess what? Uh, the history of robotic of these kinds of robotic spectrographs isn't so good.
Mm.
And so we were walking in, the good and bad of it. It's extremely difficult. Most of our predecessors were not successful, let's just say,
Yeah.
or did not meet didn't get as far as they thought they could. Yeah, they were successful, but it didn't quite achieve their goals. It's very hard to do.
Yeah.
So you might have thought we were a little crazy, and but and maybe we were, in retrospect, maybe we were, because a lot of things can go wrong. But in fact, everything went really right for us.
I mean,
And
do you
so,
have to go in there and like pull out individual robots and replace them? Is that a thing that happens? I mean, how robust is this?
so we have not we have once done that, not particularly successfully. So no, it's pretty much the original instrument that's up there right now
I see.
running. And if something stops, doesn't, one of the robots fails, yeah, it's all right. It's one out of 5,000. So we're robust against that.
Right.
But it's just really hard to get these located and onto their target. And what kinds of things can go wrong? Well, they didn't get onto the target,
Yeah.
or for some reason you didn't capture enough of the light that you couldn't get back there far enough. So actually, once we built this, we were very pleasantly surprised to see that we had better transmission through all the optics that we had than we had designed it for. That we
Mm.
actually managed to preserve a lot of the light. And our predecessors, those are, can you get it on the right target, and you get enough light? And the latter is really hard. Um, so it's easy to take a really big telescope and turn it into a small one, effectively, if you don't do things right.
Yeah, sure.
And so that's the room we walked into, where it just was really hard. And so, on one perspective, yeah, it's hard, and you've got to solve those problems. On the other hand, it is a tremendous experimental opportunity,
Yeah.
and that's why this took so long to get
But
to get.
but in steady state, then during an evening run, you're doing what, 15,000 an hour, 15,000 galaxies an hour. I mean, that's your throughput.
Something like, well, a good, a really good night, we get 200. We can get to up to 200,000 gallons.
200,000
Yeah.
throughout the night.
So, and if you think about that, I have colleagues
Compare that
here.
to what it was in
Well, Mark Davis did a study over, I think, a decade of his career, and got 20,000.
for a decade of his
For a
career.
decade of his career, and we got that in an hour.
Oh man.
Right.
Ah,
Yeah, this is a machine, and it works well. So, when look, that's how you make these advances, because you
yeah.
came up with a better instrument to allow you to do, greater, deeper, more interesting experimentation. Well,
Yeah.
okay, that's what we did. So we had to take that technological leap to get there. You mentioned
Yeah.
that this was a technological advancement. Yeah, you had to do that in order to address this question of, is the equation, is it time varying, is
Right.
this, or a cosmological constant?
Now when you first began to actually do your first light experiments, it was around 2019, 2020, right? So I guess the real world encroached on progress there too, right? I mean, the pandemic must have hit right around the beginning.
Well, we had, yeah, well, right. Well, we had a very interesting. Well, it was a very interesting project in the sense that we were, you know, you sit around, you're sitting around hoping, oh, is the government going to fund me? Is the government, are
Yeah.
my colleagues going to support this? Da da da. And so you first have to get past your colleagues. Science studies. What is a good idea? Should the government, of all, should the government? And you could spend some years waiting for that process, and that. So I was, given the keys to, I was appointed director of the experiment back in 2012. We got into the congressional budget in 2015. That's when you really know you're moving, when Congress says, yes, you're going to be funded. And then we had first light, a kind of first light in 2019. So 4 years later, we're starting.
Right.
First light doesn't mean that you're running well. It means just like, okay, I could first turn things on. We went into commissioning at the end of 2019 and early 2020. March comes along. We're about to start running. Okay, we're going to find out whether it's a cosmological constant or not. And I think March 5th, 6th, it was like, uh-oh. And we had to mothball
Yeah.
the experiment. I mean, we were, covering this thing with duct tape and plastic sheets and, enormous tarps, and
I mean,
turning off,
truly mothballing in that sense.
truly mothballing. I mean, don't want to say that we put the little, those
Yeah.
yellow,
Yeah.
those white little things, but yeah, the equivalent of that. And turning off. We have our equipment is very sensitive. It requires running at cryogenic temperatures. Yeah, turning off all those kinds of systems,
Yeah.
letting these things come up to room temperature. Anything that was in a vacuum no longer is under a vacuum. It's purged with air, and
Yeah.
it's like, oh my God, all the stuff that we just spent the last 4 or 5 years building. We don't even know when we're going to be able to run it again,
Wow.
right? We had no idea. The world had shut down, and of course, one thing we couldn't do is we couldn't put our staff at risk, not knowing, and where they're all. Up until that point, they were all working in the room together. We're all working together, on equipment, and our heads are butting together.
Sharing each other's air freely.
No, absolutely.
Yeah.
And so, what do we do?
Yeah.
So that was 2020, and so that was a pretty big gulp, I have
Yeah.
to say. So we, of course, time went on. For one thing, we learned how to run this experiment with brand new, which we'd actually not really run yet.
Yeah.
We had to go back. We had plenty of opportunity to go back to our computers. We were no longer in our offices. We were working at home, and to turn it into effectively a
Remote.
fully robotic instrument where we could run from our homes. So, which we learned how to do. We actually learned how to run this very complicated instrument from our, people's,
Wow. Yeah.
people's home offices. And then we unmothballed it starting around November of that year of 2020. So towards the end of the year,
Yeah.
we sort of undid what we did, which, but believe me, it takes a lot longer to take this, to put it back together than
Of
it
course.
did to put it to sleep. So by 2021, first of all, we started a new commissioning run, and we had something called survey validation, make sure that we understood how our instrument worked. And on May 14th of 2021, we started our data taking, which is what has led up to this conversation.
But there was a fire too, wasn't there?
Well, a year later, in fact, a year later and a month. So yeah, there's never been a dull moment on DESI. I have to tell you. Every morning I wake up to see what is in my what calamity has happened in my email since the day before. It's always
Yeah.
been exciting. I have to say, there's always, when you got 250,000 moving parts, there's always something. Um, and so, you can think of this as we're running a Bugatti or something, some really complicated, expensive, one of a kind. I mean, this is
Yeah.
a one of a kind. No one. This is a one of a kind apparatus. You can believe that it requires a full time crew to keep it running. So there's always something. Yeah. Well, a year and 1 month later from the start of that run, um, there was a start of this part of Arizona where we are, near outside of Tucson, about a 90-minute drive outside of Tucson, on a mountaintop. They have these seasonal monsoons, meaning it gets hot in the summer, and then eventually the patterns change and the winds come up from moisture comes up from, I think, from Baja, from the Sea of Cortez, and it
Mm.
comes up into that region, and you start getting afternoon thunderstorms and rains. And early on in the monsoon season, um, the water doesn't, you get storms up there, but the water doesn't make it to the ground, but the lightning does.
Yeah.
So the first couple weeks of the monsoon, we had some lightning. It hit our mountain range, which was at Kit Peak, and it started a wildfire.
Mm.
And this slowly crept up the mountain, and over the course of about 10 days, 24,000 acres, with the exception of the observatory platform where the few observatories are up there, everything black and burned to the ground.
Wow.
And I remember being up there, being a bit watching at 5 in the morning, the
It's
the
like a
web
webcam you're looking
these
at?
web cameras, and of
Yeah.
course, we were all connected and everything.
Yeah.
We could watch the fire move in, and at 5 in the morning, I think it was on June 17th, I think, something like that. Um, you can see the little see the trees burning and the brush burning, and then the power goes off. I mean, the
Mm.
webcams go blank. This is
Oh,
at
really?
we were just in a you know
That could be it, right?
that could be it. And
Hmm.
but we were very fortunate. There were about 75 firefighters up there on the top of the mountain. They saved the experiment. I mean, that whole there are 24-ish, something like that, telescopes up there. The one we're on is the largest one. They're not, but these are these are thousands of degree temperatures sweeping through, and yeah, we could have burned to the ground.
Wow.
Yeah,
But you
as it was,
survived.
we survived. As it was, we had a certain amount of ash. There was a certain amount of
Ah,
cleanup, a lot of vacuuming, but
yeah.
and we got a little bit of ash on our primary mirror, and eventually we got that off. Um, but no, we were not harmed. But
Wow.
that was a as you can imagine, we were also not running during that. We didn't have power, we didn't have internet, we
Yeah.
didn't have a lot of things. Um, and so we were off for a while. So we said, okay, this is the end of our first data taking run. Our first year was actually 1 year, 1 month. So that book. So we had a pandemic on one end and a wildfire on
Fire
the
on the
other.
other.
It was an
Wow.
exciting first year. It was
Yeah,
an
totally.
interesting
But you
bookends.
did have that 1 year's worth of data,
Yeah.
and I
So
gather that's what's informed the recent results, is that?
yeah. So we haven't actually dug into the recent results yet. I
Yeah.
mean, that was our first year. Um, of course, we had to now figure out what to do with that data. We, of course, obviously spent a lot of time analyzing it. The experiment itself, as I mentioned, it's a fairly simple, conceptually simple. So the first thing you do, you take all those spectra that you got, which through an instrument like ours, it doesn't just come out on a ticker tape or something like, oh, okay,
Yeah.
here's the spectrum. You have to go find the spectrum on your sensors, and because this is all multiplexed, and there are 5,000 of these spectra all of a sudden.
Right.
Computers, so the computer you have to have great codes, and you have to have very big computers. Um, and so you have all this raw data that comes in on one end. The other, it's basically you could put it in your Excel spreadsheet. It's three numbers. It's sort of the angles on the sky and the redshift. That's it.
Yeah.
We call it a catalog. Wow, that is but it's a very simple catalog. And then that's what goes off to get analyzed, and we look for these correlations as a function of
Right.
redshift. So the experiment's pretty simple. Once you get to that point where you just have a catalog. So, okay, so what did we find after we looked at this first year's worth of data? For one thing, we had about 6 million galaxies in this part of the survey. We're going to be looking at 14,000 square degrees, about a third of the night sky that we can see from our our observatory.
Yep.
At Kitt Peak, about a third of the night sky. But on our first year data, we didn't look at all that. This is supposed to be a 5-year survey, and this was only year one. So we're only a fifth of the way through the survey. And so statistically, it's only 1/5 of the data that we intend to collect. And ultimately, we're going to get something like 40 million galaxies in our final survey over 14,000 square degrees.
Yeah.
Now, this is a much smaller survey. It was the first year. It had 6 million galaxies in it. So what we really find fascinating about the data is it is a taste of what is to come.
Yes.
So, what do you do when you're, you don't want to be in the position of having a wrong answer? Well, there are multiple ways of having a wrong answer. One of them is you put it there yourself.
You mean through a bias of some sort?
Through a bias yourself.
Yeah.
We call it confirmation bias, which
Yeah.
is where Levy says, this number that we just got, I don't know, it doesn't agree with Saul Perlmutter. I'm a little worried, or Brian Greene is going to tell me, God, that's wrong. So I'm not going to, so there are two kinds of papers that people publish. One is, well, I agree with the standard model of whatever it is, or I so disagree with it with such statistical accuracy, I can't hide it. So there are those kinds of papers, but there aren't generally papers where it's like, this is intriguing. So because you'd say, well, intriguing means I need to go back to the
So
whiteboard.
you don't publish yet.
I got to go back to the whiteboard and see if I have a factor of 2 error somewhere.
Yeah.
You don't publish it yet. So that's called confirmation bias.
Yeah.
You tell your student, you know what? Make another plot. Make another plot. Oh, okay, I like that plot. Okay, let's publish that one. That's confirmation bias. There are a lot of ways that this comes in our physics area. If you don't have 5 sigma, you don't have a discovery. Okay, well, we don't have. We don't have 5 sigma, so
that's a measure of the statistical significance of the result, and that's the gold standard that we usually adhere to. What is it? 1 in 4 million chance, whatever it is, chance of just being a statistical fluke.
Right. So because we were trying to find out, well, okay, is dark energy this cosmological constant, or is it time varying?
Right.
Well, lo and behold, we did what was called blinding. So we did a blind analysis. So we took that catalog that I mentioned of these 3 numbers and jiggled it a little bit, so you could still see the BAO in it, but
baryon acoustic oscillations.
Baryon acoustic oscillations, but you don't get the right numbers because we messed with it, and there was
purposefully
purposely. And so one person in the collaboration did that and created this catalog that nobody knew what he did. Could do all your checks to make sure that everything is hunky dory. And then when you've gone through all these checks, and of course these were myriad, we spent a year going through the checks. What could possibly Do we get the same answer if we look in the north? Do we get the same answer if we look in the south? Is it consistent with this data set or that data set or this part of the data set? And we have different kinds of galaxies that are in this, or have different names. It's not important what the names are, but they represent different ways that we can cut the data to look at the data. And are they so a lot of things that you can check about your data without knowing the answer, because the answer is not actually that important to know whether there is something wrong with the data. And another way you can do that is you can simulate the universe.
Sure.
And you can run that through your very same computer codes that you're using for your real data. You create synthetic data. In fact, that's one of the ways you have to figure out, well, okay, I now measured this universe. What cosmology did it correspond to? And one of the standard ways to do is, well, okay, let's create a synthetic data set and see which one is most like.
Right.
And then what numbers went into that synthetic? How much cosmological constant, or did it require time varying one to look like that?
Yes.
So we did a blind analysis, and that takes time, and it takes longer because you spend a lot more time doing the checks, this is all very good. Actually, I'm not complaining. These are very good. It's just that it's a commitment to publish, I would say.
No matter what.
Kind of no matter what, because it's kind of the whole point, was to take out the confirmation bias. So I believe it was December 6th of last year, we had our big reveal. We were all together in a collaboration meeting, and somebody pushed the button and went from was finally given the link to the correct data set,
to the
real data set, instead of linking to the one that had been messed with by the one person.
Yeah.
Okay. So, and then all of a sudden, plots come up, and it's sort of like, oh, okay. And so what did we find? What we found was that we were a couple sigma away from it being a cosmological constant. It was more consistent with a time varying universe, where it was, that number changed with time, and a couple sigma. Now on its
own, like 2.5 sigma.
Well, it depends a little bit on what else you use to go along with this, because there's other information around. So on its own, nobody else, nothing else. It's only a little 1.5 sigma on its own. But there are other pieces of information, like, Big Bang nucleosynthesis, or the Planck experiment, which measure the cosmic microwave background, actually measures this in the very early universe. That's a satellite experiment, extraordinarily excellent, but it measured it at one epoch from at 400,000 years. So when you combine it with some of these other things that we think are pretty rock solid, it's about 2.5 sigma.
2.5 sigma deviation from the accepted cosmological model up until this point, which is that the accelerated expansion is coming from a constant dark energy, not one that's time varying.
That's right.
Wow.
So 2.5 sigma, you have to, okay. So, we call that intriguing, but we do not call it the D word, the discovery word. That is not, because these things come and go. And as I think maybe we just spent a fair amount of time talking about how these are difficult experiments. I mean, you're only looking back 11 billion years, I mean, so.
Yeah. At 2.5 sigma, how does one do that in terms of one part in what chance?
I think you maybe call it a part in 400 or something like that.
1 part in 400 chance that this will go away. Statistical fluke. The rest of the data will change your conclusion. And so
yes, the history sometimes is a little more frequent than that, but so I have colleagues in medical profession or whatever view. I've got a new drug, and it cures something or other, and we just to 2.5 sigma. They would say, in that profession, oh, lo and behold,
that's billions of dollars right there.
Gee, I'm going to be able to regrow my hair all of a sudden.
Yeah.
So, right. So it's different for us.
Right.
So 2.5 sigma is not enough. So we would call that intriguing. But Brian, we already have the data. I was just talking about what happened between the pandemic and this fire. It was called the Contreras fire. We've already taken 2 more years of data. since then. It is being analyzed right now,
Right now.
and we're gonna continue to run for another many years. So
Yeah.
we're going to get a lot more data. So we could already turn a 2.5 sigma result into something, you know, maybe 4 or 5. You know, it's so.
Like, what's the time scale for that
Oh, I
analysis?
would say a year. You know, from this point, last time it took a year.
Right.
This will be harder. Why? You know why? Well, it will be harder, and one of the reasons harder is that are these checks that we make. Again, of course, we'll do a blind analysis.
Yep.
Now the statistical accuracy of everything is more sensitive. And so if you start seeing little effects, you're going to have to go, oh, I have to go fix that. I see a little effect here. I got to go find where that's coming from.
Right.
And before it might have been, that's a little effect. It's not statistically significant. Well, now maybe a little effect is,
Maybe.
and that may require work. So we don't know because we're not at that point yet.
And so, can we take a look at a couple of visualizations that you and your team have put together? I think there's one fly through of the data
Oh yeah,
that
let's
you've
do
made
that.
available, and just tell us what we're seeing.
So first of all, you kind of see a smile there. That's actually the footprint of the data we've taken. You know, there's an arc at the bottom. That is just where we happen to have looked. Um, we'll eventually fill in the rest of it, but this gives you an idea of this is our first year data. This is actual data.
So those are actual galaxies that you have measured.
Actual galaxies, the locations of the actual galaxies. Now the shapes of them, their morphology is an artist rendition, but the
Yeah, can you run that again just so we can see that? Yeah.
So this is, as I said, it's actual data. You saw in that finale there that it's a planetarium show. You can go see this.
Oh, really?
I think it's called 5,000 Eyes, showing at a planetarium near you. And it's up on YouTube. You know, this thing isn't moving smoothly for me here in my video, but you know,
Yep.
you can get a nice, and you can actually put on a VR headset and fly through this.
Oh,
It
really?
is
That's cool.
so. I've done that, and it is just so cool to be flying through your own universe. I mean, we only get one of these, and you get to fly through it. This is our first year data.
Yep.
Um, and okay, so this is what our data looks like.
And can we also look at a graph? You know, the more technical, do you mind? I think we have some actual graphs which show the deviation
Okay.
from the standard cosmological constant,
Oh, yes,
so-called lambda.
Perfect.
You know,
Perfect.
yeah, perfect.
Okay, so this is kind of our paper. I mean, if you think about, well, how do scientists talk to each other? Well, you know, they're numbers and graphs, and so this was, I would say, the culmination of this first year data is we have on the bottom, you know, the x-axis here is the look back time. So this is, you can also think of, um, you know, where we are is back there at 0. So this is us down
Yep.
there at 0. And then the beginning of time would be way out on the right, a little bit off, maybe about where your you know, about where your lamp is. That would be 13.6 billion years, a little bit off to the right. So we've measured most of the universe, the history of the universe here with this experiment. So that's the first thing that you would see about this. So we've gone from 0 almost to the beginning of beginning of time. So I look at this and I go, it's not just about the data points, it's about the sweep of this cosmic history that we've measured. And then in this paper, we have chopped up this history into 7 epochs or 7 periods where we collected that time period so that there's sufficient statistics for that time period. The colors correspond to different galaxies, galaxy types that we have found. So for on the left, there happen to be the brightest galaxies, nearby galaxies.
Sure.
And the ones on the right are the most luminous objects in the universe. These are the quasars.
So far away that we can still see them. So
Super
bright.
massive black holes that were gobbling up, you know, gazillions of other stars in the early history of the universe, and were the brightest objects ever. So we can pick them up.
Yeah.
And so these are the kinds of things that we used to collect our data. And then this is broken up into 7 different time periods. What you have to look for is the flat line there was supposed to be the quote right answer.
The flat line smack in the middle. Is that?
Smack in the middle is
Yeah.
called the lambda CDM. Lambda being the cosmological constant,
Yeah.
and the rest is cold dark matter. So the lambda CDM universe is the standard model of cosmology today. But that says, lambda is a static number.
Yeah.
The curve, the dashed line that goes through the data points is the one that says, oh, that actually is the best fit to a time varying expansion rate. So that that is a better fit, and that's how you can tell that it's about 2.5 sigma, because those data points have error bars that individually don't look that significant, but when you put them all together, that's how you get the 2.5 sigma.
And am I interpreting correctly? Does this suggest that the accelerated expansion, the acceleration is slowing over time? Is that how? What's this actually telling us about the acceleration itself?
So of course we explain in the paper that we bring in other things into our data set, including the supernova and the Planck and other CMB measurements, and we put them all together. Now we have about a 3 sigma effect, maybe even 3.5 sigma effect. And then we ask the question, well, what is going on here exactly? And it looks a little bit like right at the very beginning, there was a little extra pressure blowing the universe apart. And then as this evolves, there's a little bit less. So that would be very interesting, because there are some theories that were predicted not so long after this was first discovered. One of them called quintessence, but there are a bunch of other theories that are floating around that might suggest, maybe this is a potential model. You have to, your viewers are going to be looking at and squinting at this, like, well, do I really see that? Yeah, this is what it means to be 2.5 sigma, and this is why we call it intriguing. But we're not there yet.
Right.
Now, if you take those error bars and you shrink them down a whole bunch, all of a sudden, oh, yes, you have a curve, and it would be not consistent with a line, or maybe the data points will move around; it'll be consistent with a line and not that curve.
Right.
We don't know, and that's what's so much fun about it. This is why I love doing physics. It's a detective novel that you get to read and you get to discover, and it was written by the universe. It's fabulous.
So if this does hold up, obviously theorists jump on everything really quickly.
Yeah.
So
there are
a lot of ideas already.
Are already coming out. Yep.
Yeah, but do you have a sense of the explanation for? I mean, what would this mean for the far future of the universe? Say, if this holds up.
Well, look. I mean, I would start with the distant past. I mean, maybe this is all connected with the Big Bang.
Connected to inflation.
Well, we think that. We're in our current theory that the universe started with an inflationary accelerated expansion. I mean, we went from nothing in 10 to the minus 32 seconds. We went to everything.
Yeah.
That was a pretty powerful acceleration right there. So it's not like we haven't, quote, seen this before. I mean, theoretically seen it.
Yeah.
So maybe it connects to that. Maybe there's something very fundamental about this. And I find that actually very appealing, that we're living in an epoch that is somehow tied back to the beginning of time.
Yeah. Yeah.
Okay. Where are we going with this? Well, depends on which of those models. Maybe it's cyclic. So it could be that what we actually saw, that little speed up and slow and then slow down. Maybe that's that's the first wave of an oscillation. Yeah, we're going to go back to, and then that's going to turn over and it's going to go back, and we're going to, history will repeat itself.
Yeah,
I don't know, but I like this. I really find the notion that it is we're tying back to the beginning.
That'd be very exciting.
That more appealing, because I think that might provide direction to where we should be headed with this.
Yeah, and again, most people in our audience are familiar with it, but the inflationary period, that's the dominant way of thinking about the Big Bang, involves an energy in space that does change over time. It only lasts for a tiny fraction of a second, causing the rapid swelling of space that yields the universe that we're familiar with. And then we've had this late period of energy filling space, and they've been viewed as separate by most people for a
Mhm.
long time. But as you're saying, if they kind of connect up in some way, how wonderful would that story be?
So, look, I have papers here on my desk, are so many different models. Um, and, one of them is called Mirage, and the other, I mean, they're
All thawing and freezing
thawing and
models,
thawing and
and
thawing. And yeah,
yep,
you tell me, okay,
yep,
we now hand this over to you,
sure,
Brian. You tell us the answer. We're just the experimentalists. But look, we always say experimentalists, we say the data speaks for itself.
yeah,
And so the data is speaking. We haven't quite. It's going to speak some more, as we're really excited about it. I have to tell you, the fact that we are sitting on this. I shouldn't say we're sitting. We have this data that we are now moving through our computers. Um, that will give us another factor of 3 on this in terms of statistical power. Is really just incredibly
hugely
exciting.
exciting. Yeah,
Gotta wait for it. We all have to wait for it. And of course,
yeah.
it's also, again, going to be a blind analysis. So this is just I love the excitement of this. It's just so exciting that you get to answer, kind of you ask the universe these questions.
And you're
Tell
sitting
me,
on the answer, as you say.
and
Yeah,
it's starting to speak to us. I mean,
yeah.
that's what as an experiment, I would always say. We got to ask the universe a question, and it answered us.
And so, what was it like? I'm just wondering, in the room, you said there was a reveal on a particular date,
Uh,
particular time. When people saw, I presume right then and there, that there was a suggestion of something not in keeping with the cosmological constant being constant, were there oohs and ahs in the room? I mean, what was it like in
well,
that?
they're different. They're different. I would say that there was a different collection of oohs and ahs, and depending on how you accent that, it could be ooh, or it could be ah. So there were true oohs and there were oohs, and so yes, this is and I'm so thankful we as I said that we blinded it because of that. Like, okay, this is really exciting and interesting, and we need to get this out
Yeah,
to this is really concerning, and what did we do wrong? So you have the gamut of emotions, and I think you even have as human beings you can have those same emotions at the same time about it.
yeah.
So I definitely heard that in the room.
Absolutely. Well,
Yeah,
it's so wonderful, exciting. It's so exciting to know that within a year or whatever duration of time it takes you to get it right, we'll know whether this is just a fluke or if it's telling us something deep about our cosmology,
right.
the connection to the past, and how the future may differ from what the standard model has told us. Exciting. So, Michael, thank you so much for joining us and these wonderfully clear explanations of the work that you and your colleagues have been doing and are doing and will be doing. And we'll just sit here on the sidelines with bated breath, waiting to hear what the next thing that the universe has to tell us through your data. So wonderful, exciting. Maybe we'll get to talk again, as the next iteration of your data analysis is given over to the public. So
Well, that'd be wonderful.
thank you so much.
Well, thank you.
All right, everybody, that's our conversation for today. Exciting possibility. And look, that's what cutting edge science is about. You just don't know the answer. There are hints, there are suggestions, and sometimes they go away. In the history of science, there have been many results, 3 sigma or greater, that have gone away, but who knows? This may be one of those that builds its significance over time, gets to that golden threshold of 5 sigma. And if that's the case, it will change our cosmological models. And look, as Michael was saying, that's what observers and experimenters live for. And it's what we theorists live for too, because if you're to wipe out the cosmological constant as a constant, and we know that the dark energy varies over time, that's sort of a gold mine of opportunity for theorists to jump in and come up with new and more robust models of the universe, how the universe began and how it will ultimately end. That's what this story is speaking to. That's why this all matters. That's what this is all about. So stay tuned for further chapters in this particular story. Please sign up, join our YouTube channel, sign up for the World Science Festival newsletter, where you'll be alerted to these conversations as they happen. And we're waiting for the next big breakthrough to be announced in this arena, as well as in the many other subjects that we cover in these conversations. So thank you so much for joining us. Until next time, this is Brian Greene at World Science Festival in New York signing off. See you next time.